All right, we are starting to go through review, dealing with our unit 1. So our goal today is to finish this study guide for polynomial functions. After that, there's a problem set kind of applying these base skills, and that's exactly what this sheet is. These are all of the base skills we kind of covered in unit 1. You should definitely get some practice hitting our critical thinking type problems or test type problems as well. So first thing we kind of want to point out is working with polynomials in standard form. So that is when our polynomial is completely multiplied out, and it's slightly different than factored form where we have our factors multiplied together. So what can we figure out from a standard form polynomial? Well, one of the things we can find out is the degree. That is just the exponent of the largest exponent in the problem, the exponent of that leading term. In this case, the degree is 3. And we can also find out, hey, we have a negative leading term because we have that negative sign out in front of our leading term there. With that, I'm going to kind of make a jump here. These two things kind of both tell us what end behavior to expect. 3 is an odd number, and we have a negative leading term. So I should expect that my graph is going to kind of have that mismatch of behavior where as it goes left, it goes one direction. As it goes right, it goes the other direction. And it is going to kind of decrease as we go because we have that negative aspect of it. Then the total number of zeros, roots, and solutions, that's also going to stem from our degree. We should have 3 total 0 roots or solutions. And lastly, our y-intercept, that is just going to be the last component of our equation, which is negative 12. We can find all of this from graphing. If I type this into Desmos really fast, go f of x equals that negative x to the third, check that I have plus 2x squared plus 11x minus 12. I can kind of zoom out a bit and explore all this different stuff. So we can see that, hey, I have that negative end behavior that lines up. I have 3 different zeros. I'm not worried about where they are right now. And I have a y-intercept at negative 12 here. So we can also learn a lot from our factored form of a polynomial. And actually, this is the same exact graph as what we just did. If I throw this in there, we can kind of see what's going on here. Negative x minus 3. Oops, sorry. X plus 3. I have x minus 1. And I have x minus 4 as my 3 different factors. You can see that if I toggle that on and off, we are dealing with the same graph or the same function. However, we can learn some different things from this. So degree we can find out is 3 again because we have 1 factor, 2 factor, 3 factors involved. So we do have a degree of 3. Our leading term in this case is going to be negative because we have that negative sign out in front of my factors. The number of total zeros, roots, and solutions, we should have 3 as well, 1 for every single factor that we have in our problem, which again, we have 1 factor, 2 factor, 3 factors. And that end behavior, since we have a negative leading term, we have a degree of 3, we should still be able to find out that, hey, it should have that negative odd behavior or decreasing behavior. And lastly, we can find our actual zeros, roots, and solutions. And keep in mind, we can only find the ones that are real. There are some instances of finding imaginary ones, which we're going to kind of fast forward to in a little bit. But if we want to find the real solutions, we can look at each factor. And if I look at x plus 3 and I set that equal to 0, okay, that means I have a 0 at x equals negative 3. If I have a factor at x minus 1, we can kind of flip that sign. That means I have a 0 at x equals positive 1. And lastly, if I have a factor of x minus 4, we have a 0 at x equals positive 4. These are our real zeros here that we can find from our equation, and that is our x-intercepts. So just want to check this out, confirm that all that lines up. We've already talked about degree, total number of zeros, and behavior, and that sort of thing. So just checking out our zeros here on our graph. If we look, there indeed is a 0 at -3, +1, and +4. So if we're given factored form, we can find the standard form by multiplying. I'm going to do the box method with this problem just because a lot of you like to set it up that way. I have a 2 by 2 multiplication problem, so I'm going to set up my box with x plus 4 on the left side, x minus 2 on the top. X times x gives me x squared, minus 2 times x gives me minus 2x. 4 times x on the bottom left, and -2 times 4 is -8. I add up all these terms outside of the box here, and I get x squared. Looks like I have some like terms to combine with the 4x and the minus 2x, so I'm going to say that's plus 2x and minus 8. So just going to throw that function notation out in front of it to confirm. And again, we could always graph this if we need to in order to say, hey, does the top one match the bottom one? If we've done it correctly, it should work. We'll try that with example 4. So in this problem, we do kind of have to split it into 2 multiplication problems. We're going to handle this portion first. And I'm going to do this in blue to kind of color code it. So I have a 2 by 2 problem. I got x plus 3, x minus 1, so that gives me x squared minus 1x, positive 3x in the bottom left, and minus 3. If I add that up, I get x squared plus 2x minus 3. And I'm going to take that and I'm going to multiply it with this other factor here. So that's the one that's left over. So I keep my parentheses around that. I then multiply with this x minus 3. And I'll set up this box on bottom. I have x minus 3. And up top, I have x squared, 2x, and minus 3. So I'm going to multiply x squared times x is x to the third. And I get minus 3x squared. Then I get 2x squared minus 6x minus 3x and positive 9. I made a mistake on this earlier, so I'm going to quick just double check my answers. Cool, I think I got that right. So if I add all this stuff out and rewrite this, in fact, in our function notation, I get x to the third power, negative 3x squared plus 2x squared is going to be minus x squared. Then we have a minus 9x plus 9. And let me just double check this in Desmos real quick to see if it lines up. I went ahead and I typed in my original equation, x plus 3 times x minus 1 times x minus 3. Here's the equation that we just multiplied to. So it'd be x to the third minus x squared. It looks like a minus 9x plus 9. And boom, those line up good. So we did multiply that correctly. Moving on, we can go the other direction. If we're given standard form, we can find factored form. There's 2 different ways to do this. We can either factor by hand or we can graph. Factoring by hand, if this is over your head, don't freak out about it. You can always do this with graphing. If I look at example 5, I need to find 2 numbers that add up to 8 or multiply to 18, add up to 11. So I'm multiplying to 18, adding up to 11. And if I look at that, I think 9 and 2 should work. 9 times 2 gives me 18. 9 plus 2 gives me 11. So that factored form is just going to be x plus 9 times x plus 2. In example 6, I have that difference of squares. That's what's happening here in example 6, where I have an instance of, all right, 64 is just 8 squared. And so I can rewrite this as a product combination of x plus 8 times x minus 8. And lastly, we have an instance of greatest common factor in example 7, where it looks like I can take a 6x squared out of everything. So if I divide out that 6x squared Inside, that leaves me with a 3x and minus 1 because that is all that's left over. And if you guys think about it, if we multiplied back in, that 6x squared times 3x would give us 18x to the third. 6x squared times -1 would give us that -6x. Again, those are pretty quick skills, but if you want to do this graphically, super simple. Plug into Desmos, find those zeros, rewrite those as factors. We should check end behavior and multiplicity at the end of each problem. We'll kind of see that when we get to example 10. Let's start working on example 8 though. So I type this in, get f of x equals x squared plus 2x minus 8. So I got this typed in. Now I'm looking for my zeros. My zeros are where my x-intercepts are. I'll zoom this in a little bit. I have an x-intercept at -4 and 2. So I'm going to quick note that, hey, I have zeros at -4 and 2. So if that's the case, then that means my factor there for the 0 at -4 is x plus 4. We have a factor for the 0 at positive 2 is x minus 2. And I'm just going to rewrite that function notation. And we have two factors. The degree is 2, so that looks good. We should have that positive end behavior. Let's just plug it in to check it real quick. We have x plus 4, x minus 2, and boom, those things line up, so we're all good to go there. With this next problem, example 9, there's going to be a little tweak at the end, but let's start it the same way. Throw it into Desmos, check out, see what's going on. So I have negative x to the third minus x squared plus 9x plus 9. I think that's right. Plus 9x minus 9, and this negative was flipped as well. So I look at this graph. I have zeros at -3, positive 1, and positive 3. So I'm going to write those zeros out. We had -3, positive 1, and positive 3. So that factored form equation, we can start writing as x plus 3 times x minus 1 times x minus 3. However, we're going to want to check the end behavior and multiplicity of this. I see that I have a negative leading term, so my guess is that we're going to have to throw a negative in front of that first factor. Let's just check this out though and see if I got that right. So we had an x plus 3, an x minus 1, and an x minus 3. Yeah, you can see that all of our zeros lined up, boom, 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 but that end behavior is way off, right? They're going in opposite directions. So by throwing that negative sign out in front, which also showed up in our standard form, we can ensure that we get that factored form correct. All right, the other thing we got to look out for is multiplicity. This I set up in a separate section because I really wanted to point it out. When a factor shows up multiple times in the equation, it's called a multiplicity. This shows up as us bouncing off the x-axis. So if I write this example 10 problem in here, we got negative x to the third power plus 3x squared, and that last thing is a minus 4. You'll notice that, hey, we should have 3 zeros because I have a degree of 3. However, I only have a 0 at -1 and -2. All right, so let me just write that real quick. Zeros at -1 and 2. But if you look at the 0 at 2, notice how this one bounces off our x-axis. Okay, so that has a multiplicity. That means it shows up twice. So I'm going to make a quick note here. Hey, this thing shows up twice. So as I'm writing my factored form, I have my f of x equals x plus 1 for that first factor, x minus 2 for that second factor. But since it shows up twice, I'm going to throw an exponent up there. And last thing I should do is just check to see if I got this right. It was x plus 1, x minus 2 squared. It looks like my zeros line up right, but again, I don't have that end behavior matching, I noticed that my leading term out in front has a negative, so I got to throw that negative out in front here as well. So let's just make that final update to our factored form here. Okay, moving on to this idea of imaginary versus real zeros. We talked about real zeros very briefly already. Three key concepts. If zeros, root solutions are real, they're going to show up as x-intercepts on our graph. So these instances here, those are real zeros. Anything that's remaining, those are going to be imaginary. All right, we can't see them. We just got to know how many to expect and then count. I'm going to ignore this last part until we finish example 11. So if I look at example 11, I see I have a degree of 5. So I'm going to write that in. And then the way I can find the total, so I know the total zeros root solutions should be 5 as well. The way I can find the number of real zeros is to actually type this in and inspect it. So I go in here, I got f of x equals 4x to the 5th plus 5x squared minus, looks like 3x. And I look in here and it looks like I have 1, 2, 3 real zeros. That's it. I only have 3 real zeros. I'm going to put a quick note here from graph. So if I have 3 real ones and I have 5 total, that means 2 of them have to be imaginary. Now, the last component here, imaginary zeros, always come in pairs. That lines up with this last statement here, right? We have 2 imaginary zeros. We don't have 1 or 3. But the imaginary component is always reversed. So if we know that we have a 0 at 1 minus 2i, then the other 0 is going to be at 1 plus 2i, where 1 is kind of our real component here, and 2 is our imaginary component. Okay, the real stays the same, the imaginary is reversed. So in example 13, similarly, that other imaginary 0, we have the real component at that negative 2, the imaginary component is negative 4i. Okay, just a couple more things to run through. Solving polynomial equations, we're going to take this equation in example 14. We're going to do it again in example 15, but we're going to do it algebraically first and then graphically second. This is a weird one. The first step we got to do when we are solving polynomial equations, we have to move everything to one side of the equation. It's different than all of our other ones. So when we do that, we see that all of our stuff is over here on the left. I want to move this 2x over to the left side with it. So what I'm going to do is I'm going to subtract it from both sides. Notice how I'm stacking up those like terms underneath each other. I get x squared minus 8x plus 12. And if I subtract everything from the right side, I'm just left with 0 over there. Then we can rewrite that polynomial in factored form. So in this case, I can do my I can either do it graphically if I want to, or I can do my sum and product puzzle where I'm multiplying to 12, adding up to negative 8. And if I do that, I should have a negative 6 times negative 2 combination to get me there. And so that means that I have x minus 6 times x minus 2 equals 0. And if I go ahead and solve that, we can solve that by finding the zeros because that's what our right side is equal to. That tells me that I have solutions of x equals 6 and x equals positive 2 by way of flipping that sign or setting it equal to 0 and solving. If we're going to do this graphically, first off, make sure you're using that NC test version of Desmos. It's not going to let you do it the way you think you can do it in the regular version when you get to the test. So we're going to plug each side of the equation separately into Desmos, and this is a good skill to have just in case you forget the math. So if I cut my equation down the middle, I say, hey, this is going to be my left side. I'm going to go f of x equals that left side, x squared minus 6x plus 12. And then I'm going to go that right side, f of x equals 2 of x, or 2x. And I'm just going to find out where does left equal right. That's my question that I'm trying to answer. So we are trying to find that intersection there. So go f of x equals x squared minus, what was it, 6x plus 12. And on the other side of that equation is f of x equals 2x. If I zoom out and look here, it looks like I have my two intersections. One of them has an x value of 2. One of them is an x value of 6. So x equals 2 and x equals 6 are my answers here. Okay, last concept we're talking about, and this is definitely kind of the most tricky concept that came up in our unit, is the remainder theorem. It says when a polynomial f of x is divided by x minus c, then the remainder is just the value of that polynomial at c. Ignore all that, okay? All we're trying to do is if we are dividing by a factor, we plug in what we think the zero might be. So if we look at this problem, we have if x squared minus 3x minus 4 is divided by x minus 2, all we're going to do is we are going to plug in a positive 2 here. Plug in 2. If I look at my next example, example 16, okay, we're given the same function, x squared minus 3x minus 4 is divided by x plus 1. In this case, we are going to plug in -1. And what we're doing is we're trying to see, hey, is this a factor? Is it a 0? If it is, our function is going to evaluate down to 0. So we can either write this out and do, hey, our f of 2 equals 2 squared minus 3 times 2 minus 4 equals, so that gives us 4 here, minus 6, minus 4. So that would give us a -6 as our remainder. Or what we could have done as well is we could have typed this into Desmos, the original function f of x equals x squared minus 3x minus 4. And then we could have gone in and said, hey, what is the f of 2? And again, it gives us that -6. So in this case, since our evaluation or remainder is -6, that means our graph is not hitting 0 at the x minus 2 or at a 0 of 2. If you look at x equals 2 on your graph, you notice that our graph is not 0 there. So in this case, no, x minus 2 is not a factor. If I look at this next one where I plug in -1, let's just quick check that real quick with our Desmos, f of -1, we should get 0. Let me confirm as we kind of go through our more mental math, f of -1 equals -1 squared minus 3 times -1 minus 4. That will give us +1 plus 3 minus 4 equals 0. So that's our remainder, in which case x plus 1 is a factor. So if we look at the graph there, we should be able to see that as well, where, hey, at a value of -1, my graph zeroes out. So that means that x plus 1 is a factor there.